Welcome to part 2 on propositional logic. What is the difference between syntax and semantics? What is syntax? What are semantics? Syntax refers to grammatic rules that govern the construction of Boolean formulas. The rules that we use are parse trees and in-order traversal of the parse trees that help us define what a Boolean formula is. Semantics, on the other hand, are the functional interpretation of a formula. Namely, we take a Boolean formula and we view it as a representation of a Boolean formula, just as a truth table represents a Boolean formula. Now, the whole point in using syntax is that it helps us provide well-defined semantics. Namely, our goal is, given a formula, to define a Boolean function that this formula represents. Now, we need to assign semantics to logical connectives. Okay? Let me give you the following example. Look at the following 5 letters, T-A-B-L-E. We read this word as table, but so that would be the syntax. This is a noun, and it is just pronounced table. What does this table mean, actually? Well, its semantics could be either a table, like a desk, or it could be a table in which we fill in data. So the word table, which is syntax, has 2 different meanings, which are semantics. Of course, we're not happy in Boolean formulas if we would have a Boolean formula that has 2 different meanings. Okay? So the situation in natural languages in which words have several meanings is undesirable when we talk about synthetic constructions like Boolean formulas. Okay, so given a logical connective, we can view its role either in syntax or in semantics. What is the role of a logical connective in syntax? It is a glue. It takes 2 Boolean formulas or 1 Boolean formula, and it helps us construct a larger formula from a small formula. What are the semantics of a logical connective? Well, the semantics is just a Boolean function that assigns a truth value based on the value of this truth function, on this Boolean function. Now, to emphasize the fact that we have a logical connective and we have a function which is attached to this logical connective, we can use a different notation for both. So suppose I have a logical connective here denoted by star, and suppose that this logical connective is a k-array connective, namely it's either, in our case, unary or binary. Now, we want to define or denote the semantics of this logical connective, okay? So we're given this logical connective and we want to denote the function, the Boolean function that is attached to this connective. And we denote this Boolean function by capital B subscript star. And this is, of course, a function defined over k-bit strings because the connective is k-array, and it assigns values which are 0, 1. Let us see 2 examples. For example, consider the binary connective AND. Then the Boolean function that corresponds to AND gets 2 parameters, B1 and B2, each of which is a bit, and returns the AND of these 2 bits. What about the NOT connective? The NOT connective is attached a function B0. This function B0 is defined over single bits because NOT is a unary connective, so K here would be equal 1. And the value of B0 when given input B is just the NOT of the bit, namely 1 minus the bit. We also assign semantics to variables and to constants. The semantics that are attached to a variable are simply the identity function. So the function that corresponds to a variable x is the identity function. It receives a bit b and it returns the same bit. The function that is attached or associated to a constant sigma, where sigma is a bit, is the constant function. So regardless of the bit b that is given as input, it outputs the value sigma. Okay? So I could write here, for example, b0 of 1 equals 0. b1 of 0 equals 1. Notice, the 0 here is determined by the 0 here. The 1 here, let's change color. The 1 here is determined by the 1 over here. Good. Now we want to define what truth assignments are. So suppose I have a set of variables u. A truth assignment is simply a function tau defined over u, and it assigns to every variable in u a truth value, namely a bit, 0 or 1. Consider the following example. A is a variable that denotes today is Monday. B is a variable that denotes this is written in blue. So the truth value of A would be 1 because today is a Monday. The truth value of B would be 0 because this sentence is written in gray, not in blue. Okay? So to every variable, we can assign a truth value. Our goal is to extend the truth assignment tau from the domain U to the domain of all the Boolean formulas over the set of variables U with respect to our favorite set of connectives C. Thus, a truth assignment to variables becomes a truth value for every Boolean formula. So if I have my tau over here, which says tau of A is 1 and tau of B is 0, then I can extend it to tau hat of A or B becomes 1 because A is 1. Tau hat of A and B is 0 because tau of B is 0. Tau hat of not B is 1 because tau of B is 0. Okay, so let us define how this extension works. So we're given a formula P, and we are given an assignment tau, a truth assignment tau. We want to define tau hat over the formula P. Tau hat is the extension of tau. How do we define tau hat of P? We use an algorithm. The algorithm is called eval. Eval has three parameters, g and pi, which denote the parse tree of the Boolean formula P, and tau is our truth assignment, which tau hat is supposed to extend. Now, eval is an algorithm that also employs in-order traversal over the parse tree. Let's see how this algorithm works. I will start with a graphical depiction of what the algorithm does. I'm omitting the pi, the labeling of the nodes in the parse tree on purpose. So, consider the parse tree of our formula G, of our formula P, denoted by G, and the truth assignment tau. So G, let me emphasize, is a parse tree of the formula P, and tau is our truth assignment. Okay, now how does this algorithm work? Consider the following cases. The base cases, these are the base cases actually. The base cases are that P is simply the Boolean formula 0, 1, or a variable x, where x is just a variable in the set capital U. Well, if our formula is simply 0, then the evaluation is always 0. If our formula is 1, the evaluation is always 1. If our formula is x, then the evaluation is tau of x, this tau. So this will, of course, be inside the set 0, 1. It's a bit. Very good. Now we have reduction rules. We have two types of reductions. The first one holds when the root of the parse tree has an in degree of 1, In this case, we know it's labeled by a not. Let G1 denote the parse tree that hangs from the root. Then we apply the eval recursively over G1. We get a value. This thing is a value, a bit in 0, 1. And now we want to know what is the not of the evaluation with respect to tau. So this would just be tau of, not, let me erase this because it's confusing, not of the eval of G1. Okay? There's a tau here. Let's fix it. Good. So we evaluated G1 based on our assignment tau. We got a bit as an answer. This is inside 0, 1. And we take this bit and now we invert it. This is the outcome of eval and not on G1 with respect to the assignment tau. Good. Now, what happens if our formula is the AND of two subformulas, the parse trees of which are G1 and G2? Then we apply the evaluation recursively on G1 and G2. We get eval on G1 with respect to tau. I have a mistake here. Let me fix this. This should be like let me erase here this fellow, and let me erase this fellow, and now it's correct. Good. So I do the evaluation with respect to the subformula, the parse tree of which is G1. I get a bit. So this is a bit. Sorry. This is a bit. And this as well as a bit is a bit. So I get two bits, one from the evaluation of G1, the other one from the evaluation of G2, and I do the AND of these bits because in the root I have AND. What would have happened had I had in the root an OR? Then I would have done the OR of these two bits. Okay? Let's go back to the listing of the algorithm to understand what it does. The parameters of the algorithm are the parse tree, which is the pair G pi, and the truth assignment tau. The algorithm is recursive. It has base cases and reduction rules. The base case holds when the parse tree consists of a single node. In this case, the parse tree is one of three things. It's either a constant, one of two things, sorry. It's either a constant or a variable. If it's a constant, then you just read off the value of the constant in the root and that you return this value. If it's a variable, then you return the truth assignment over the variable. Now the reduction rules, there are two types, one in which the integrity of the root is 1, the other one in which the integrity of the root is 2. If the integrity of the root is 1, we know that the root is labeled by not. We apply the algorithm recursively to the subtree hanging from the root with the subgraph G1 and the labeling pi1. Pi1 is simply the restriction of pi to the set of variables in G1. And tau is the same truth assignment we were given as input. We apply the evaluation recursively, get a bit sigma, and we return the not of this bit. If the integrity of the root is 2, then we have two subtrees hanging from the root. We restrict the labelings to each of these sets of variables v1 and v2 to obtain pi1 and pi2, and then we execute the evaluation algorithm recursively over these two subtrees g1 pi1 tau, g2 pi2 tau, to obtain two bits denoted by sigma 1 and sigma 2. We take these two bits and we compute the function b pi of r of g. This is the function. Sorry, I cannot point to it. I'm sorry. The last line, return b pi of r of g. This is the Boolean function that corresponds to the connective that appears in the root of the parse tree of our formula. And this Boolean function, which has arity 2, is applied to the two bits sigma 1 and sigma 2. Now, think of our evaluation procedure. This evaluation procedure receives two types of inputs. The first one is our formula pi. Actually, instead of the formula, we feed it with a parse tree of p. And the second input is our truth assignment, tau. Now, since we have two types of inputs, we can play a game in which we fix one input and let the other one vary. So we have here two variations. In the first variation, the truth assignment is fixed, and we plug in any formula we wish, and therefore the output will be the extension of the truth assignment to the formula p. Thus, every formula now attains a truth value which is either 0 or 1. On the other hand, what we could do is we could fix the formula and let the assignment vary, in which case what we're actually doing is we are computing a Boolean function denoted by b of p over the bits tau of x1 up to tau of xn, assuming that our set of variables is x1 up to xn. Therefore, this function will get as input n bits, if this thing is indeed n, will get as input n bits and output a single bit. This is the evaluation of the function with respect to the truth assignment, tau of x1, tau of x2, up to tau of xn. Let's define three definitions: satisfiability, tautology, and logical equivalence. So let P denote a Boolean formula. We say that P is satisfiable if there exists an assignment tau such that tau hat of P equals 1. Here in this diagram, you see the evaluation. This is P, and I require that there exists a tau such that the outcome of the evaluation will be 1. P is a tautology if the value tau hat of P equals 1 for every assignment. So you see here the picture. We have our evaluation procedure. We have the formula P, and we require that for any assignment tau, the outcome of the evaluation procedure is 1. Two formulas P and Q are logically equivalent if tau hat P equals tau hat Q for every assignment tau. So here we have the picture. We have P, we have Q, we have an assignment tau, and we require that for every tau, if we evaluate P with respect to tau and we evaluate Q with respect to tau, we will always get the same value. Then we say that these formulas are logically equivalent. Let's see some examples. In the first example, we want to show that the formula phi, which equals x XOR y, is satisfiable. Indeed, let's plug in tau of x equals 0, tau of y equals 1, then tau hat of 0 XOR 1 is 1, and there exists in truth assignment tau such that the truth value tau hat of the formula is 1 as required. Let's consider the second example. Let phi denote the Boolean formula x or not x. This is a well-known formula. If I let x denote to be, then this formula actually says to be or not to be. This is phi. Now we want to claim phi is a tautology. So we need to show that for every truth assignment, the value of tau hat of x or not x is 1. Now, there are two truth assignments because x either attains the value 0 or the value 1. Now, if x has value 0, then not of tau x has value 1. If tau of x is 1, then not of tau x is 0. In either case, the OR of 0 and 1 is 1, and the OR of 1 and 0 is 1, and therefore the formula x or not x is a tautology. Let's consider two formulas, phi and psi, where phi is x XOR y, and psi is not x and y, or x and not y. We want to show that these two formulas are logically equivalent. It's very important. Logically equivalent. Okay. To do that, by definition, we need to show that tau hat of phi equals tau hat of psi for every truth assignment tau. How do we do that? We enumerate all possible truth assignments. How many truth assignments do we have? 2 to the power of the cardinality of u. U in this case consists of two variables, x and y. So we enumerate here all the possible assignments to x and y. Could be 0, 0, 1, 0, 0, 1, 1, 1. And now what we do is we write the truth value of x, not x and y, the truth value of x and not y. We have 4 possibilities. We take the OR of these two, so the OR of 0 and 0 is 0, the OR of 0 and 1 is 1, and so on. So we get here the truth value of psi. You should focus on this column. On the other hand, let us look at the truth value of phi. Truth value of phi is simply the XOR of these two bits. And you see that these two columns are identical, and therefore for every truth assignment, the truth value tau hat of phi equals tau hat of psi, and therefore these two formulas are logically equivalent. Let us play with the definitions to see what we have obtained and to practice the definitions. Consider a Boolean formula phi. We claim that phi is satisfiable if and only if not of phi is not a tautology. Let's see how we prove this. I want to emphasize that in the proofs, all the transitions are by definition. So, phi is satisfiable by definition means there exists a truth assignment such that tau hat of phi equals 1. Now, let's see the connection between the second line and the first line. If tau hat of phi is 1, then what is not of tau hat of phi? Well, not, what it does is it evaluates tau hat of phi and does the not on it, right? Sorry. From the beginning. Let's see this line compared to this line. Tau hat of phi is a bit. Okay? So, if we negate both sides of the equality, negation of 1 becomes 0. Negation of tau hat of phi becomes not tau hat of phi. Okay? So, we transition from here to here is by negation of both lines. So all we did was not. Let's explain the transition from the second line to the third line. The transition from the second line to the third line is simply by the definition of tau hat. How does tau hat evaluate not of phi? It evaluates phi and then it applies the not operator. So this is by definition of eval. Okay, now let's look at this line. There exists a truth assignment such that tau hat of not of phi is 0. This means that not phi is not a tautology, because if it were a tautology, then for every truth assignment, tau hat of not phi would be 1. Okay, so this is again by definition of tautology. Now, assume that the set of variables is x1 up to xn. Our goal is to view a truth assignment over these variables as a Boolean string and vice versa. Good. So let's present the following definition. Consider a binary vector v that consists of n bits, v1 up to vn. Use this binary vector to define a truth assignment over u. The truth assignment is denoted by tau sub v. The domain of tau sub v is a set of variables, x1 up to xn, and it assigns a truth value to every variable. Tau v of xi is simply vi, the corresponding bit in v. Let's consider the following example. N equals 3, so this means that u equals x1, x2, x3. Now, I have my binary string 0, 1, 1. So, tau v of x1 is the first bit, 0. Tau v of x2 is the second bit, 1. Tau v of x3 is the third bit, 1. So I get a truth assignment over the three variables x1, x2, x3, which is defined by the binary vector v. Now, you see that what I did was I took a binary string and I mapped it to a truth assignment. I claim that this mapping is a bijection from the set of all binary strings to the truth assignments defined over the set of variables x1 up to xn. This is an exercise. Check it. It's an important exercise. Okay. Now, what I'm going to do is I'm going to take a Boolean formula P over the variables u, where u is again x1 up to xn, and I'm going to use this Boolean formula P to define a Boolean function b sub p over the set of variables 0, 1 to the n. Okay, what is the definition of BP? BP for the set of binary strings v1 up, binary bits v1 up to vn is the extension of the truth assignment tau sub v, where v, I remind you, is the vector v1 up to vn. So I take this vector, I use it to define a truth assignment, I extend this truth assignment and apply this extension to the formula P. Let's see an example. Suppose P is the formula x1 or x2. So, now I'm interested in various truth assignments. Let's consider the first truth assignment, which is defined by the string 0, 0. So this means that x1 is 0, tau of x1. And this means that tau of x2 is also 0. So I do 0 or 0, and I get 0. Here, I say tau of x1 is 0. Here I say tau of x2 is 1. Therefore, BP of 0, 1 is the OR of 0, 1. The OR of 0, 1 is 1. Namely, every Boolean function, every Boolean formula defines a Boolean function. Okay? This is how I did a transition from syntax to semantics. Okay, now, what I did here is I described the mapping from Boolean formulas to Boolean functions. Okay? Now, these Boolean functions are defined over binary strings of n bits, if indeed my set of variables consists of x1 up to xn, if I have n variables. Okay? Now, the question, an interesting question, is whether this mapping is one-to-one and whether it's onto. By one-to-one, I mean that if I have two formulas which are not equal, and P1 maps to the function f1, P2 maps to the function f2, I want to know whether it means that f1 is not the same function as f2. Now, I want to emphasize, when I write equality of formulas, I mean that the two formulas are the same. They have the same parse tree. I'm not referring here by equality to logical equivalence. Logical equivalence is a different thing. Equality here means same parse trees. Okay? So here, if they're not equal, that means that they have, sorry, let me change color. That means that different parse trees. Okay? It's not logical equivalence. Here, when I ask whether this mapping is onto, I'm asking, is it true that for every function f, there exists a Boolean formula p such that p maps to f, namely p of p equals f. Okay? Good. Every tautology induces a constant function. Let's prove this. So consider a Boolean formula. We claim that it is a tautology if and only if the Boolean function b sub p is identically 1. Namely, b sub p of v is 1 for every vector v of n bits. Let's see how the proof proceeds. P is a tautology if and only if, for every truth assignment, tau hat of p equals 1. Now, we have a bijection between truth assignments and binary strings. So we can replace tau by binary strings and view instead of view tau as the truth assignment induced by tau sub v. So tau sub tau, for every tau, there exists a v such that tau equals tau of v. Right? And for every v, there exists a tau such that, again, tau equals tau of v. And this is true because tau of v is an assignment. And if you want to know what is the binary vector that corresponds to v, then you just take tau of x1, tau of x2, tau of x3, and so on. Good. Now, something is stuck here, badly stuck. Just 1 second. Here. Okay, so for every truth assignment, I can find a binary vector v such that tau equals tau of v, and vice versa. Good. So this means that for every binary vector, tau hat of v, when applied to the Boolean formula p equals 1, and this, by definition, is the binary function b sub p. So it means that this function is a constant function 1, because for every vector it attains the value 1, and this is exactly what we wanted to prove. Consider a formula p. We claim that p is satisfiable if and only if the Boolean function b sub p is not identically 0. Namely, there exists a vector v such that b sub p of v equals 1. Good, let's see the proof. If p is satisfiable, then there exists a satisfying truth assignment and vice versa. Good, if there exists a satisfying truth assignment, then there exists a binary vector that induces a truth assignment that satisfies p, and vice versa. If there exists such a vector v, then of course that the truth assignment that it assigns satisfies p. So we're between the second line and the third line. But this is exactly that. This is the definition of the binary function induced by p. Finally, two Boolean formulas, p and q, are logically equivalent if and only if the Boolean functions bp and bq are identical. Namely, for every vector v, bp of v equals bq of v. Let's see the proof. P and q are logically equivalent, means that for every truth assignment they get the same truth value. Now we can replace truth assignments by binary vectors because there's a bijection between binary vectors and truth assignments. That would mean that the truth assignments induced by every binary vector assign the same truth value to P and Q. And again, we can replace tau hat of V by BP, tau hat of V of P by BP of V, and tau hat sub V of Q by BQ of V, because by definition, the binary function BP of V is the evaluation tau hat of V of P. This completes the second part of the chapter on propositional logic. Thank you.